Here we have a square ABCD with this side 1. Inside the square there is a right triangle EFD. One of the vertices of this triangle, vertex E, lays on the diagonal AC. And we also know that the part of the diagonal EG, the part that lays in the triangle EFD, is twice as long as segment AE. And we asked to find the area of this right triangle. So the way we're going to proceed is, first of all, let's divide this triangle into two triangles. We're going to have the blue triangle and the yellow triangle here. Together, they give us the whole triangle we're interested in. The next thing we're going to do, we're going to connect point A and F. And we're going to get four triangles here. Our original blue and yellow, but we also get gray and pink triangles. Together they're going to give us one big triangle, AFD. So first of all, let's look at the blue triangle and the gray triangle, triangles that lay above the diagonal AC. Let's compare their areas. Well, we know the area of a triangle is half height times the base. So let's drop an altitude FH. This is an altitude or height of both blue and gray triangles. And the areas of those two triangles will be half that altitude FH times, in case of blue triangle, this side EG, and in the case of gray triangle is the side AE. And since AE is a half of EG, what we find from here that the area of the gray triangle is a half of the area of the blue triangle. In a similar manner, we can show that the area of the pink triangle is a half of the area of the yellow triangle. The next thing, notice that the triangle AFD, the big triangle, consists of four triangles, gray, blue, yellow, and pink. And that's what we have here. And now what we're going to do, we're going to use these two formulas to calculate the area of a gray triangle and the pink triangle. And if we do, we're going to have that the area of the big triangle AFD is 3/2 of the area of the blue triangle and the area of the yellow triangle. But those two areas together give us the area of the triangle we're interested in. And that is triangle EFD. And that's what we have here. So now all we need to do is to find the area of the big triangle AFD. In this case, we can quickly find the area of the triangle EFD. But the area of big triangle AFD is actually half of the area of this square. Why is that? Well, first of all, let's just drop an altitude in the big triangle, altitude FK. And now what we find that the area of the big triangle AFD is half the altitude FK times the base AD. But FK equals to AB and equals to AD, and both of them equals to 1. And therefore the area of this triangle is going to be half. Now if you plug this half into previous equation, we can quickly see that the area of the triangle EFD is 1/3. Interesting observation is that originally we were given that the triangle EFD is a right triangle. But if you look at the solution to this problem, we actually never use the fact. In fact, it doesn't really matter that this triangle is a right triangle or not a right triangle. So because of that, I really don't know why the author of this problem insisted on having triangle EFD as a right triangle. But if you have some ideas, please post some comments here.